Hi everyone, my name is Chris Handley. I'm a senior OLE engineer at Arcadis based in York. Arcadis are experienced in the support of rail infrastructure delivery, providing all design services across all disciplines and stages. This presentation is going to be focused on the light rail project Metro Flow. So Arcadis were commissioned by Buckingham's to produce the Form A, Form B and AFC OLE designs for the Metro Flow project for the main client Nexus. The role of principal designer was fulfilled by Buckingham's. The line was handed back to Nexus in December 2022 and services have been running since then. The project was named Major Project of the Year at the National Rail Awards and it scooped Outstanding Engineering Achievement at the Global Light Rail Awards. I'll briefly discuss the project aspects of 1500 volt DC over OLE and some of the technical challenges we had. So this is a map of the Nexus Tyne and Wear Metro network. The Metro project started, Metro Flow project started at the Pelaw chord, which is between Pelaw and Hebburn stations, and finished just after Bede station. So this shows the site P works. So the top track there in blue is an existing network rail line, which runs from the Pelaw chord to the Praxoil terminal. So that runs adjacent to the Metro tracks, which is shown in yellow. The existing Metro tracks were dualled around the stations, so you can see Hebburn and Jarrow station, and they were dualled at the extents of the site too. So between those areas of dual tracking, the Metro tracks were just a single bi-directional line. The existing OLE in these areas was cabled between the respective OLE switches. For the project, the network rail line was to be incorporated into the Metro network to ensure that there is dual track throughout. So now the freight train services which run to the oil terminal would run over the Metro tracks. 5 crossovers have been added through the route. This allows the freight train to cross to the outline between the junctions. It also allows for bi-directional Metro operation when the freight train is partially in the fuel terminal. The freight train being so long that when it goes to unload in the terminal, part of it would still be on the main lines. So that was one aspect of the project, and another was to increase the system-wide weekday frequency of the Metro services to every 10 minutes. So some of the scope items that we went through for the project. So the Nexus existing OLE system is 1.5 kilovolt DC OLE. They've got areas of heavy OLE, which is twin catenary between Pelaw and Hebburn, and then from Hebburn to Bede it was just the standard OLE with single catenary. We needed to put new OLE over the former network rail line, new OLE over the new crossovers, and replace those cabled sections of OLE with aerial OLE. We had to renew the OLE on existing structures, so even if the existing mast and foundation were retained, we replaced the existing cantilevers. There was a slight increase in the OLE scope to include the renewal of the OLE through Bede station. So that just involved replacing the cantilevers and the wires. To accommodate the freight train, which was a W6A gauge, we had to increase the nominal contact wire height through the route from 4 meters to 4.5 meters. This was challenging around some of the low bridges, so we had to fit some of those bridges, Victoria Road, Station Road, which is in between the Hebburn station platforms, and Monkton Terrace. The track loads at Monkton Terrace to accommodate the OLE were very high, 600 mil, and the track gradient there was like 1 in 65. For the existing structures that were being retained to accommodate the new double insulated OLE, we had to install earth rods to remove the existing bonds to the track. We agreed with Nexus a derogation for on their OLE standards for the REFOS to accommodate some low REFOS existing structures, so we didn't need to replace those. There was also a provision for a future station at Bilkey, which is between Peelaw and Hebburn, and all the switchgear was renewed, including the Hebburn and Chichester substations, which were now ground-mounted isolators. Just some project info. So it was about 13 single track kilometres of OLE, 17 wire runs, 114 new structures installed with 48 existing structures removed, and 116 existing structures reused. And the route covered 3 existing stations, which were Hebburn, Jarrow and Bede. So Nexus have their own set of standards which we needed to work to. So this includes the overhead current collection equipment technical specification, which covers standard OLE parameters, the bonding standard and system earthing policy. The overhead current equipment technical specification covers REFOSs, contact wire heights, grading, electrical clearances, pan sway and other parameters. I just included there a snapshot of the section which on the contact wire heights, which shows the differences between joint user and metro only tracks. So as you can see, the minimum height there for the where it's exclusively metro vehicles is very low, and we had to raise a lot of the wire heights to fit in the W6A gauge freight train. I've also added a section there on the electrical clearances too, because this the DC electrical clearances tend to be lower, so the normal static clearance there is above 150 millimeters and passing clearance of 100 mil. Although you can go lower if you get Nexus's agreement. Nexus also have set of like historic technical calculation and gauging drawings, which are useful for like understanding the design of their own legacy equipment. So the new OLE that we used on the route was from the Siemens SciCat design range. So the existing Nexus OLE equipment and component record drawings are now obsolete. So we proposed the use of Siemens SciCat LD equipment, which is suitable for 1500 volt DC OLE with both double insulation and twin catenaries. So this equipment has also been used recently on the Edinburgh Tram project. And there's just a snapshot from the kind of Siemens product catalogue of one of the like 3 kilovolt DC composite insulators. So OLE structures can be single or double insulated. So here are 2 examples. The pictures are taken from Gosforth Depot. So single insulation in the single insulations in the cantilever frame, where in that situation the mast is insulated from the ground and bonded to the traction return rail. So the mast is held in the concrete foundation with like a insulated proforma. So if there was a failure in the single insulated insulation, the fault current would go back to the rail. And it also means that the mast, the OLE structure, is the same potential as the rail. So we were introducing double insulation in the area of works. So the two ways we achieve this. So one is you have primary insulation in the cantilever frame. Again, so that's just the insulator by the mast, and then secondary insulation in the registration equipment. So this involved a insulated or GRP registration tube and an insulated catenary support. In this case, the mast is then earthed through the foundation, so it's just a piled foundation with the mast directly bolted to it. For the existing retained structures, the existing mast bond to the traction return rail was removed, and a local earth pit was proposed to bypass the existing insulation between the mast and foundation. So double insulation helps mitigate the risks of insulation failure and the mast becoming live and stray current leakage. So stray currents are another issue in DC systems. So DC traction systems can cause stray currents which could adversely affect the railway concerned and outside installations when the feed and return circuits are not sufficiently insulated from earth. The major effect of stray currents is corrosion of metallic structures, where stray currents leave the metallic structure. There's also risk of overheating, arcing, fire, and subsequent danger to persons and equipment both inside and outside the DC electric traction powered supply system. So this is predominantly where some of the return current leaves the rail and would pass through an adjacent parallel metallic kind of structure and then re-enter the rail after that. So for this MetroFlow project, we had to create some standard kind of cantilever arrangements. So we produced a series of standard push-pull cantilevers, which we were modified from a reference design to suit Nexus system parameters, in particular the lower system height of 900 millimeters. So the reference design was the cantilevers used on the Edinburgh Tram project, and we developed these with the client and Siemens to what you see in front of us. So Siemens advised to keep a minimum angle of 1 in 3 in the diagonal tube. Then we drew them up with different back distance values to suit a range of reach values, ensuring clearance to the pantograph. So one of the effects of squashing the cantilever in this way is you need more variations in back distance, which suit a smaller kind of selection of cantilever reaches. A civils check was then undertaken to confirm the tube sizes and the cantilever geometry was suitable and the requirement for an auxiliary strut. So these cantilever designs were then presented for comment to Nexus, Buckingham's and Siemens in the OLE system description, which was produced to accompany the Form A. So you can see on the left there, we've got a direct attachment style where the registration tube's directly connected to the diagonal tube of the cantilever, and then a more standard pull-off cantilever. And this is the push-off cantilever arrangement. To ensure the buildability of the cantilevers on the detailed design cross sections, we showed additional details and notes which covered the components of insulator assemblies where the composite insulator wasn't suitable, and additional construction information. So the cantilever selection details showing the direction of the eye clamps, and they denote where in the single catenary areas, which hole in the twin catenary clamp the single catenary goes into. So the twin catenary OLE system. So we needed to replace the existing Nexus twin catenary OLE equipment. This had an additional catenary wire terminated into the centre of the compensating plate at a reduced tension to increase the current carrying capacity of the OLE. The main catenary and contact wire were nominally tensioned at 11 kilonewtons. However, over time, the tension in the wires has equalised with tensions as low as 5.9 kilonewtons measured in the contact wire. A recent Nexus renewal project fitted a new termination arrangement to the twin catenary system, which divided the tensions from the existing Ballet rates slightly differently. So this gave 7.5 kilonewtons in each catenary and 6.5 in the contact wire. This arrangement was deemed not to provide enough tension in the contact wire for purposes of the complying with deviation in the longer OLE spans. So Arcadis proposed a new termination arrangement to avoid the issues with the legacy system. The twin catenary wires are terminated around a pulley to maintain equal tension in the wires. The contact wire and catenary pulley are now terminated onto a compensating plate for which we produced a basic design for. So the compensating plate divides the tensions from the total tension provided by the balance weights into the wires. So in this case, it divides the tensions unequally so that to give the required tensions in the catenary. The twin catenary wires are separated by an offcut of contact wire attached to PG clamps, so they don't clash with each other. So in this new arrangement, both catenaries are tensioned to 8.2 kilonewtons and the contact wire is tensioned to 8.9 kilonewtons. So this is a similar setup to the old Mark I system, which is suitable for line speeds of up to 120 kilometers per hour with multiple pantographs. So this is in excess of what Nexus required for their system. The line speed in the area varies from about, I think, 60 to 80 kilometers per hour, and Nexus wanted to have provision for 20 kilometers of overspeed, bringing the total requirement to 100 kilometers per hour. So this arrangement and solution was presented to Nexus in workshops and then put in the OLE system description. At the detailed design, we did move one of the sets of one of the insulators to the sleeper edge. As you see, it requires two for the double insulation. So to provide tension to the twin catenary OLE system, we needed to produce a balance weight anchor system. So the requirements are that the OLE has long tension lengths. As I say, the increased OLE scope meant that we had to renew 2 tension lengths through bead station. Some of the existing half tension lengths were about 850 meters there. Through the rest of the project, the maximum was under 750 meters. But as per Nexus standards, we had to accommodate a large temperature range. So this included 40 degrees of current heating because the DC current tends to heat the wires more. This can lead to a lot of long track movement. As it's a metro system, the termination wire heights are also quite low. As I say, the nominal in-running contact wire height was about 4.5 meters. So the termination wire heights were maybe 5.2 meters. So the longest tension lengths required balance weight movement of over 3 meters. So to accommodate this, we developed a balance weight anchor system to tension the twin catenary OLE system. This design has a twin weight stack to maximise the vertical movement of the weights. In some locations, we provided a rotated design to prevent gauge infringement or sighting issues, like the one on screen. I produced like a spreadsheet just to check the balance weight movement and confirm there was enough room beneath the weight stack as well. And we got Siemens to produce balance weight setting charts where the datum was set at the maximum, the minimum temperature. So this allows for the maximum room for movement beneath the weights. Yes, this is just a photo of the existing, the old equipment that we've replaced. So as you can see here, the equipment is over 40 years old, and over the time the wires have stretched, and you can see the existing balance weights are in a single stack, and I think they're resting on the ground. So this would cause the tension in the wires to reduce as the temperature of the wires increases due to the balance weight movement being restricted. So part of the twin catenary system was twin catenary droppers. So originally we wanted to allocate Arthur Fleury twin catenary droppers. However, they were unavailable when we needed them. Therefore, we produced a basic design based upon Siemens SICAP components. So Siemens already had a style for twin catenaries, twin catenary current carrying droppers, but the dropper hoops were for larger 120mm squared catenary wires. So we produced a basic design where the hoop was made smaller to fit the standard 70mm stranded catenary wires. For the reduced encumbrance locations, we produced another basic design, and this was based upon a design used in the Manchester Metro link. So this had the contact wire clip supported by a V dropper, where both ends of the dropper wire connected to the catenary, the twin catenaries. So this design was presented to Nexus and amended to incorporate their comments. So we changed the contact wire clip there to a sliding dropper clip, where this has a kind of metal hoop is a lot bigger, and it has a plastic insert, which is to reduce wear on the dropper wire. So that is the end of what I wanted to talk about. Does anybody have any questions?
Yeah, any questions at all? There's none in the chat at the moment. I've got a general one just while people are thinking of one. The track lower you talked around, the 600mm.
Yeah.
Was that a particularly troublesome structure? Could the structure be rebuilt or not?
There were a number of discussions around this Monkton Terrace bridge about, as you say, whether it's worth rebuilding the bridge or not. If I remember correctly, if you think about starting kind of low chainage, that maybe a few hundred meters away there is an underbridge, so you couldn't reduce the height of the track there. So that meant the kind of gradient of the track had to be very steep when it went through the bridge to obviously provide clearance to one the kind of closest face. The track gradient is so steep that there's a noticeably better clearance on the kind of high chainage side, and you can see the effect that that's had on the earthworks required in the area. There's a sheet pile wall on the outline side, and on the inline side there's the just a graded slope there. So the track gradient there was about 600mm, I think, dig depth, which was the worst case, and the track gradient was 1 in 65. That caused some issues. So when you've got very steep track gradients like that and changes in track gradient, you need to assess like the vertical loading at each of the OLE supports to make sure it is downwards, because otherwise they wouldn't be able to achieve kind of the contact wire heights that you're proposing, because the tension conductor won't be able to get down in the way that it is designed to be. For us, the vertical curves were kind of after the bridge, so they're behind where this photo is taken from, and they kind of go from, then the track goes from very steep downwards to kind of almost level as it goes over the A19 bridge, which is behind us.
Just building on that one, Chris, but on Transpennine or kind of network rail infrastructure, we'll look at these voltage control clearances. Did you minimise the clearances from that perspective here?
So how do I say it? So yeah, so new OLE standards for 25 kV AC mean that you can apply surge arresters and really reduce the OLE clearances. Because this is the DC OLE, we already have can use the very low OLE clearances. Right. So of about I think it was 150 mil static and 100 mil passing clearance. So the main issue we had on this bridge, Monkton Terrace, and also Victoria Road, Station Road, where it was the arches, is the pantograph. So the Nexus pantograph is, from their record drawings, it's 1700 mil across. We derogated the values of pantograph sway, which are written into their standards, to use a lower value from the group standards. I think is it 2173.
I've got a hand up from Mark Stowell. Mark, have you got a question?
Hi, Dave. Yeah. Hello. Thanks, Chris. Thanks for that presentation. Superb. Good to see. I've got a couple of questions related to the voltage. I'm familiar with the Manchester Metrolink system, and that's a 750 DC volt DC system. When you talked about stray current, would that be significantly different in terms of its potential and its potential to be stray, as it were, and damage potential? Would that be significantly different on this system, which is 1500 volts DC?
I think that when the voltage is lower, the kind of current can be higher, in the sense that stray currents would be worse in the 750 volt DC systems than the 1500 volt DC systems.
Right. Okay, that's interesting. I mean, I've got no electrical knowledge whatsoever, so it's good to know. It's good to know basic things. And another sort of second point to my question was, you've gone through some stations, and I guess do you review touch potential through there, and is that significantly different from values from sort of heavy rail touch potential assessments where it's 25,000 volts?
So yeah, there are a number of structures in the station. So yeah, how do I put it? For Hebden Station and Jarrow Station, we removed the existing OLE structures and replaced them with new OLE structures. I think they were mostly TTCs, so they were you have a mast on one side of the track, and the cantilevered boom supports both the OLE over both lines. And by doing that, we could Hebden Station, you see the platforms are staggered, so we could put the OLE structures on the other side of the track to the station. In Jarrow, we put them in places where they're not easily accessible by people. At Bede Station, we just reused the existing structures, because we just had to, the scope of works was just to renew the OLE. So we renewed the headspan wires and OLE conductors. And for those station structures, we retained the existing bond from the mast to the rail.
I see. And is a sort of a touch potential assessment for, you know, the pantograph, as it were.
Yeah, so
off the
standing
platform.
surface clearances.
Yeah.
Yeah, so how do I say it? The 1500 volt DC, if you look into the particularly into the British standard, where is it 50122, it's classed as low voltage. So the clearance is by envelope to the from a standing surface is smaller than what it would be for a 25 kV system.
Yeah.
So the wire heights in the stations are lower than what you'd experience in like a 25 kV project.
Yeah.
Off the top of my head, the contact wire heights at the stations, but most of them were restricted by the bridges. There were bridges in both Hebburn and Jarrow, but about 4.2 meters.
Okay, no, that's great. Thank you for that, Chris. I'm grateful for that. Thank you.
Okay, any other questions? I'll bring it to an end. Maybe just a prompt. Well, I'll advertise the next meetings, but Chris, thanks a lot for stepping in and giving such a comprehensive presentation. It's good to see what else is going on and what challenges there are elsewhere. So virtual round of applause, or people could have mic and wolf whistle if they wish, but I'm sure that's acceptable these days.
Yeah, thank you very much. I didn't realise how quick it'd been.
No, very comprehensive. Thank you. Just next meetings. I think I've just been. I think we've got one on the 15th of February. Understanding wheel set contamination on track circuit performance. Is that from Northern, Richard? Is that?
It's from via Northern, yeah, but it's from Will Skipper, University of Sheffield.
Oh, okay, University there. And then maybe kind of linked with this, I think on the 18th of April, we've got a presentation from Pete Summers on Metrolink as well. So a bit of an overview on the system in Manchester. Will's asking where they can access this recording. If you go on YouTube and put in PWI, there is a channel there where you can find it. Will, I think you might sometimes link to a professional wrestling. Or is it a gaming session? I don't know, but normally it goes to the PWI for track. We can put it in the link anyway, can't we, Richard?
Yeah, and you can also get it through the website. There's the archive for the website. If you remember, you can get access for it that way as well.
Yeah, for the normal webpage. Oh, okay. Thanks everyone for joining. Hope you've enjoyed it. Join us next time. Unless there's anything else, Richard, I'll.
No, we've covered everything. As I say, there'll be an email coming out shortly with this year's programme for up until August. So keep your eyes peeled for that. And if anyone wants to present, then just give me a shout, drop me a line, or speak to the PWI.
Right. Thank you.
Thanks, Dave. Thanks, Chris.
Thanks, everyone.
Thanks, everyone. Thank you.